Alright, this is the last video on Maxwell's equations in integral form. We're going to be talking about Ampere's law and then finally the Maxwell addition to Ampere's law to create the Maxwell-Ampere equation. So Ampere's law states that if we take a vector line integral of the B field dotted with dr, so in other words the B field dotted with our path, that's going to equal, and we go in a closed loop, that integral is going to equal the permeability of free space times the current enclosed within the membrane. And you might be thinking, well, what membrane? Because this is a vector line integral, so there's nothing here that says membrane, it's just a path, right? Well, if you have taken Calc 3, you'll recognize Stokes's equation, Stokes's law, which states that we can relate some integral like this, some vector line integral like this, we can relate that to the double integral of the curl of the field times ds. And I kind of lost border in there, but anyhow, if you remember the curl, take a look at this membrane, and the curl is going to be measuring each little segment's rotation. And Stokes's theorem proves that each one of these little rotations summed up cancel out except for on the perimeter. And so what you end up with is this vector line integral, which is actually describing what's going on inside of its membrane. So imagine taking this curve and drawing a membrane throughout the ring. And the interesting part of this is you can actually choose the shape of the membrane as long as it connects on the line integral here. You could really have it pop out like this or like that, or you could expand it. As long as it's connected here and there, there will still be current going through only once. And so that is Ampere's law. Turns out it's not entirely correct. And the reason why is because of this thought experiment that I think Maxwell came up with, which is this. If you can choose the membrane, as long as it connects to the edges of the line integral, then, for example, you could use a capacitor. So here I have two plates of a capacitor drawn, and the capacitor, before it's charged, you could pass a current through this line integral, through the loop there. You could pass a current through it, but you could stretch the membrane in between the plates of the capacitor. And what this does is it just screws everything up, because now there's no current passing through the membrane, right? The current is here, but because the membrane's out here in between the two plates, there's no current passing between the two plates. So we've now just proven that in this case, the line integral of b dot dr does not equal mu sub naught I enclosed. That's what E and C stands for, is the current enclosed. But in fact, in this case, based on where we put the membrane, it actually equals 0. And that's a problem. So the next idea that Maxwell had was, well, maybe because I know there's going to be an E field in between that's passing through the membrane, right? There's going to be an E field between the plates of the capacitor. And as you start charging a capacitor, the flux will increase until it reaches a maximum. So the E field flux through this will increase until it reaches a maximum. So what we're looking for is let me make some room here. What we're looking for is some term that's going to help us make this not 0 when we have it in this configuration. So what we're looking for is because this term, the mu sub naught I enclosed, there's no current going through this membrane, so that goes to 0. So what we want is some other term. I'm going to call it big X. And we're looking for this term to be a good substitute for mu sub naught I enclosed. And so if we want this big X to be equivalent because we still have the same current passing through here. So our new term x had better take up the slack that's being dropped off by the current here because it's not actually passing through the membrane. So the first step here is we're going to go ahead and say, I could write mu sub naught I could write that as mu sub naught change in the charge with respect to time, because current is dq dt. And this charge would have to be enclosed. So now we've rewritten this as mu sub naught times a change in q enclosed with respect to time, change in charge that's within with respect to time. And now we're going to take a look at one of the first equations that we learned, which is Gauss's equation, Gauss's law for electricity, which states that the electric flux through a closed surface is equal to the charge within the surface divided by the permittivity of free space, or E sub naught. And so you'll notice here Q enclosed, Q enclosed. So I'm going to go ahead and solve for Q enclosed. First I'm going to say I can rewrite this double integral of E dot dA. I can just rewrite that as the flux, the electric flux. And then I can multiply epsilon sub naught over. And therefore I've proven that Q enclosed is equal to epsilon sub naught times the electric flux. So I'm now going to substitute Q enclosed for Q enclosed. And what I end up with is I end up with mu sub naught times the derivative with respect to time of the permittivity of free space times the electric flux. Now you'll notice here that because E sub naught is a constant, I can pull it out. Remember, this is equal to my unknown kind of fudge factor here, so I can pull out E sub naught because it's a constant, and what I end up with is mu sub naught times E sub naught times the derivative of the electric flux with respect to time. So in other words, the change in electric flux with respect to time times our two most important constants in electricity and magnetism is going to equal this x term. And there's a name for this. It's called the displacement current. And I think why they call it that is because when we moved this membrane, we displaced the current. So the current was no longer going through the membrane. And so what that meant is that we needed to find a displacement current that could make up for that membrane and where we put it. So now that we know that, we do remember the original Ampere's law had this mu sub naught I enclosed term. And now we have this other term, this big X term, which we're calling displacement current, plus the displacement current. And this is now our new law. This is called the Ampere-Maxwell equation. And remember last video about Faraday's equation, I was saying, that they found out first that a change in magnetic flux created an induced electric field. Well, now they had evidence that a change in electric flux could actually induce a magnetic field. And it was at this point that Maxwell got the light bulb going on, and he used both of these equations to actually extrapolate the speed of light using these equations. And in doing so, he really didn't think that it was a coincidence that the speed of light, as had been measured in the day, popped out of his equations with these specific constants. So he kind of immediately thought, this must be what light is. Light, it's chargeless, it's massless, at least as far as this course is concerned. Well, it doesn't have a charge yet. It's this propagating electric field that's creating a changing magnetic field, which in turn is creating a changing electric field, which in turn is creating a changing magnetic field, and that just keeps going. It doesn't need charge. It doesn't need any sort of medium to travel through. It's traveling through itself. It's creating the E field for the B field to travel through, and the B field's creating the E field. It's this like self-propagating thing, and it's pretty cool. And this is the equation that cracked the case. And so I hope this was helpful, and I'll see you next video.